look then at the outcome of these reactions, the radical monohalogenations. So we took methane plus chlorine gas, and we zapped it with ultraviolet light, and we made chloromethane. Hey, see how that reaction doesn't balance? It's organic chemistry, we don't care. We don't balance equations anymore. We have other ways of torturing you. We're going to make you write mechanisms. And in the mechanism, you're going to account for every ion and every atom. So when you just write out the line thing, hey, this turns into that, we're not going to bother balancing. Oh, what happens to the other chlorine atom? It's lost. Okay, so that's as simple as it's ever going to get. This part is technically a little bit difficult, because what you would do is these are both gases. So let's simplify to something else that's a liquid. You'd get a vessel, and I would put my alkane in there, and then I would allow it to be in the presence of chlorine. Oh, by the way, chlorine is a gas that is heavier than air and green. Fortunately for us, it's green and incredibly toxic. If we spilled chlorine in this room, or we generated a lot of it, which you can do at home in your lavatory, it's not particularly difficult to do because some household cleaners contain chlorine, and you can evolve that chlorine by mixing it with other household chemicals. People often do it inadvertently in the toilet. If we were to release a giant amount of it right now, that would be a good time for everybody to stand on their desks, and then we could watch the green cloud go down the stairs like this and asphyxiate everybody on the ground. But we'd be fine. So we wouldn't let this be an open container. We would have to seal this somehow or control the pressure in this. And then I need an ultraviolet light bulb. Ultraviolet light bulbs, usually mercury lamps, are moderately expensive, have very, very high power consumptions, and give you skin cancer if you let them shine on you, and make you blind if you look at them, which actually happened at my previous university, where one of the graduate students was doing an experiment and opened the box to see how well the experiment was going, and the ultraviolet lamp gave her a cataract. She's only in her 20s, so it took a couple of months for her to get her eyesight back, but she was blind for I think about 3 months. So we don't look at this, and we don't let it be anywhere near us, and this is kind of toxic. And here's where it gets really, really bad. Glass absorbs 100% of ultraviolet light, which is why you can be driving in your car on a very hot sunny day and you experience the heat from the sun because the infrared passed through the glass, but you will never get a sunburn inside your car, except the elbow that you stick out of the window. That's the only thing that's going to get burned, because glass absorbs 100% of it. So we have to make this out of a very special borosilicate glass that is incredibly expensive. that allows the light in. And then the magic happens, you make a radical, and the radical just tears through everything. You make a small concentration of radicals and just let them go. They're incredibly violent in reaction. Okay, we have to put that in a big box. We probably have to cool this as well. Really, really super cold. I used to put a solution of acetone and dry ice through this, like negative 40 degrees Celsius, and then wrap this, and then put it in a fume hood, and then completely wrap the inside of the fume hood with aluminum foil. And then just hope for the best. So a little bit problematic. There are a couple of other things that we can do. We can generate the radicals with a spark. Probably don't want to do that because our feedstock is probably flammable, possibly explosive. So we don't want that. So these reactions take a little bit of care. We have a much better way of doing it. There is a molecule called N-bromosuccinimide. Oh, I should have looked in the book before I came out. It's kind of an ugly ring with another ring that comes off it, and then a nitrogen, and then we're going to put the bromo on the nitrogen. Don't need it just yet. Succinimide. That's, we may have been, if we've read the book, we might have been suspecting an amide, but this one is an imide. It's a little bit different. And what that does, take my methane, it puts a bromo in there. This is the source of one bromine radical. We can do it just in a tube, in a, we don't want to do it in a beaker, is a source of bromine radicals. Which is nice, because it's our easy way of doing these monohalogenations. And then we realize that doing the reactions the hard way and doing reactions the easy way on the very, very simplistic level have no difference. But once you start making the molecules a little bit bigger, we start to deviate in what we get from the first way to the second way. And here's why. Chlorinations are very, very fast. That's good. Fast reactions means that I can achieve my product quickly. Hey, if it takes me an hour to make 1,000 liters of chlorohexane and it takes your company 1,100 hours to make the same amount, oh wait, did I get my numbers mixed up? How much did I say the first time? Scratch that. If it takes me an hour to make 100 liters of chlorohexane and it takes you an hour and 10 minutes, I win, you go out of business. So a radical chlorination, hey, that's good. Brominations are slower. This is going to reveal the first time that we're going to see this. I think I may have said it at some point. Fast reactions imply, so I really shouldn't do that because that's the retrosynthesis. Means indiscriminate. I don't know how to spell that word. Discriminant. Is it indent or that? Ask your English class. brominations are much, 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 much slower. And therefore, selective reactions that go slowly are much more likely to settle on the lowest energy product. Reactions that just grab the first thing that they can find are likely to make the most available, easiest option. Reactions that have time will give you something different. Now, when I do it just with methane, I only have one carbon, so I don't see the outcome. But when I start to do things like this, let me just keep this a bit short. I'll get right to the point. If instead of methane, the feedstock for my reaction was this molecule, name 2-methylpropane. Remember, I'm only allowed to put one chlorine into this molecule. That's the product that I get. It's not the only product that I get. There is another smaller product in there, but that's the product that I get. When I do the same reaction with bromine, the bromo group goes there. What's the name of the product of the radical monohalogenation of 2-methylpropane? What's this called?
1,4,2-methylpropane.
What's the name of the product of the radical bromination of 2-methylpropane? What's this called?
2-bromo-2-methylpropane.
2-bromo-2-methylpropane. There's not a gap there. It looks like there's a gap. These are covalent molecules. When do you leave a gap in a chemical's name? Give me an example of the name of a chemical that has a gap in its name. Space. There is no space in 2-methylpropane, and there is no space in 2-bromo-2-methylpropane. There is a space in sodium chloride. When there's a separation of charge, I've got a cation and an anion. The space tells you this is ionic. The lack of spaces tells you this is a covalent molecule, not an ionic compound. Tell me one reason why. No, you wouldn't. Never mind. I was going to say, oh, this one might be chiral, but clearly not. Different outcome. This is the better product. That is the most available. Here's why. We are going to look at the hydrogens that are in this molecule, because again, it's the hydrogens that are being substituted here, and classify what kind of carbon are the hydrogens attached to. So this is the hydrogen that just got substituted. It is no different than this one or that one, right? All three of those hydrogens on that methyl are the same as each other. Yes? Okay. Is that hydrogen any different than this hydrogen? Nope. Or that one, or that one, or this one, or that one, or that one. In 3D, I have got a carbon that is tetrahedral, put hydrogen pointing back, and then it has methyls. And these methyls are all the same as each other. When we start learning about NMR, we're going to see that we cannot distinguish between those three methyls. They are identical to each other. What type of carbon is that hydrogen attached to?
Primary.
That's a primary. And that's a primary. And that's a primary. Are we all cool with what primary means? Primary carbons attached to one other carbon. So I drew this first molecule out down here in 3D. What about that carbon right there? That's tertiary. And tertiary is attached to 3 other carbons. Now, the reaction progresses, and at some point, this hydrogen gets plucked off and leaves the radical on that carbon. If we were to list radicals based on carbon in order of energy, we would find that tertiary carbons are a better place for radicals than secondaries. Tertiaries are better, and secondaries are better than primaries. Draw that out. R is any carbon containing group. So this reaction with the bromine makes the most stable product. The one with the chlorine makes the one that's most available, because count the number of hydrogens. Hydrogens are the things that are going to get replaced here. This has 9 primary hydrogens and 1 tertiary hydrogen. The indiscriminate reaction is going to go, I'm going to take what's available. So the reaction with the chlorine goes to the place it's first available. I outnumber the tertiaries, which is the best place, 9-1. Therefore, that's where I put the chlorine. Here, same thing. I've got 9 primary hydrogens and only 1 tertiary hydrogen. But this reaction is slow and is going to pick the most stable. So this here is the most stable. And this is the most available. And when you do your reaction fast, you go with what's available. And when you do your reaction slow, you go with what's stable. Later on, because none of our books want to dwell on these radical reactions, because I'm going to tell you, we're going to see them now in this part of the chapter, and then we're not going to see them again until we do polymerizations in chapter 28. Okay, it's a long, 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 long way away. We are going to learn this as reactions that go fast and take the easy path. That's called kinetic. Speed, kinetic. And reaction paths that go the sensible, energy way are going to be called thermodynamic. My recorder just stopped. No, still going. But not looking good. Okay. So there's a bit more in there. If you read the chapter, there is a really nice, simple piece of math where it says the probability of you catching a primary versus a tertiary is this number. So given a molecule that you take apart and say, oh, it's got 18 primary hydrogens and 14 secondary hydrogens and 3 tertiaries, you can then figure out where's the how many products it's going to make and what ratio those products are in your final product. Okay? Okay, I think that's enough for the radical part, because again, we're not going to see, it's probably just 1 or 2 questions. The mechanism will be a standalone question, and then maybe a question about where does the chlorine versus the bromine go. That's a better question. All right, let's talk about alkenes. So chapter 7 shows alkenes and how they react, and then chapter 8 tells you how to make them. I'm not sure that's the best logic. I think you should probably learn how to make things and then react them, but let's just kind of follow that path. Anyway. Okay. Alkenes. We've seen them already. Don't have to really revisit this too much. They have formula CnH2n. They contain a carbon-to-carbon double bond. And that contains a sigma and a pi component, which gives you an sp2 system that is rigid. This is important. And trigonal planar. So a couple of people made this kind of mistake on the first test. They wrote a molecule, they put a double bond in it, and then they showed me wedged bonds coming up off that ring. This is not possible. That is all planar. Anything that has a double bond is stuck into 120 degrees, 120 degrees, 120 degrees, planar, flat. You don't have bonds coming up or away. Everything is in the plane of the paper, okay? All right, it's that pi bond that we're going to be interested in. So the sigma bond, we've already seen this, comes from direct overlap of the p orbitals. And then I have a pi component that goes along with it that sits here, and it's kind of a three-dimensional peanut on the top and on the bottom. And this is our area of high electron density. When we look at reactions, we're going to break our overall reactions down into smaller parts, and each of these smaller parts is going to build into an overall mechanism. It's going to be a mechanism with elementary steps in it. And each of those elementary steps is going to contain a curved arrow, and that arrow is going to have a double barbed head, arrowhead. The arrow itself is motion of 2 electrons. And at this end, there needs to be an area of high electron density. And at this end, there needs to be an area of low electron density. Okay? Things at this end include put it first because this is the chapter that we're in. Double bonds. The pi component of a double bond is an area of high electron density. Arrows come away from double bonds. Anything with a negative charge. Got a negative charge, then you probably already have a lone pair of electrons, and now you've got something negative. Or a lone pair of electrons. Basically, what we're looking at here is something that we might have considered in general chemistry to be a base. Bases make bonds. 3 definitions of a base. What are they?
Lewis.
Let's do that one last. We've got Arrhenius, Lowry Bronsted, and then Lewis. The Arrhenius definition of a base is removes H plus from concentration from solution. Because an Arrhenius acid is anything that increases the H plus concentration in solution. The base just removes it. Lowry Bronsted said that an acid was a proton donor. That makes a base a proton acceptor. That's fine, but none of these are going to work for us in organic chemistry. It's the Lewis definition that works for us. A Lewis acid was an electron pair acceptor. That makes a Lewis base be an electron pair, lone pair of electrons. Has to be a pair of electrons. Look for the lone pair. Look for the negative charge. Look for the pair of electrons that are in the pi component of the double bond, not the sigma bond. So this scribble contains 2 electrons shared between 2 atoms in that sigma bond right there. They don't break. The number of times, 1,262 pages in the book, the number of times that we break a carbon-to-carbon sigma bond in the book is so small that when it happens, it's going to be notable. When carbon makes chains to itself, those chains usually perpetuate. It's very rare that we break a carbon-to-carbon sigma bond. Really rare. But 2 electrons from here? Oh yeah, they can go. They're movable. That molecule didn't really need them to attach the carbons together. We just put them there as extra. They can go. So look for the 2 electrons from the double bonds pi system. The 2 electrons that are really a lone pair that are giving the molecule a negative charge are just the regular straightforward lone pair. This is a base. It's going to reach out and grab hold of an acid. How do I recognize what an acid looks like? It probably has positive charge because it's electron deficient. Somebody's taken the electrons away and left a positive charge behind. Or it could be that this is an atom attached to an electronegative atom that's experiencing electron withdrawal by, we call that induction, electronegativity. Okay. So these are things that you would have considered from general chemistry to be acids. Okay. Bases reach out and grab acids. Our fundamental example of this is there's a hydroxide. It's got a negative charge because it's got an electron that doesn't belong to it. And it's going to take one of those lone pairs of electrons and reach out to something that is experiencing electron withdrawal. High electron density, low electron density. Base, acid. Okay? So bases and acids are fine, but those words already exist and they have a very definite meaning. Bases attack acids, and acid has been defined, 2 out of the 3 definitions call an acid H+. So if our arrow goes to a hydrogen, our behavior is a base. If it goes to anything other than a hydrogen, we're going to use a different word for it. So if hydroxide attacks a hydrogen, we call that base acid behavior. However, if it reaches out and grabs hold of a carbon, let's have this bonded to bromine, we now call this nucleophile. And electrophile. A nucleophile, electrophile are the blanket terms that going to use all of the time in organic chemistry, and some of the time our nucleophile is being a base because it's attacking a hydrogen. Most of the time we're going to see them behave like nucleophiles when they attack a carbon. All right. So I have an alkene. It's got an area of high electron density. That means it's going to be on this side of the arrow. It's going to react with things that belong on this side of the arrow. Let's start out with the very, very simplest one. Let's throw in some acid. The thing that I'm erasing now on the board, there is nothing more important than that. That's the most important thing that I will say to you in the 30 weeks of organic chemistry. There is a base. The base senses the presence of an acid and it reaches out and grabs that acid. Okay, in every single step of every single reaction on every page of the book. If you don't get what an acid and a base is, you can memorize the 1,262 pages in the book. If you truly spend a little bit of time figuring out what an acid and a base is, and you've had a year up to this point to get here, you can look at any of the equations, any of the mechanisms in the book and go, hold on, yes, I see it, yeah. That's where the electrons are, that's where the electrons want to be. I'm going to draw a line from one to the other. Okay, we're going to learn by doing how to recognize that. And that means we don't have to memorize stuff. Okay, so alkenes are going to react by this generic reaction. Alkenes, let's make a note. That's an area of high electron density. And it has a unit of unsaturation. That's all I need. Those two pieces of information tell me which of the 5 mechanisms I told you about, whatever day that was, Monday, which of the 5 mechanisms I'm going to do. I have an area of high electron density, and I have a unit of unsaturation. My 5 available reactions are nucleophilic substitution, nucleophilic addition, electrophilic substitution, electrophilic addition, and elimination. 5. The fact that I have an area of high electron density high electron density is on the left-hand side, low electron density on the right-hand side. I have an area of high electron density in the alkene. Is it going to react with electrophiles or nucleophiles? Electrophiles. Areas of high electron density react with electrophiles. My alkene has an area of high electron density. Therefore, it will react with electrophiles. It has a unit of unsaturation. My reactions, possibilities are substitution, addition, and elimination. I could be a nucleophilic substitution, electrophilic substitution, a electrophilic addition, a nucleophilic addition, or an elimination. It could be one of those. But I have a unit of unsaturation. Molecules with units of unsaturation are probably good.